All right, so welcome to day two of our Electronics Hardware Design Masterclass. I am Professor, and once again, I'm happy to be your tutor. In today's episodes or sessions, we will basically run up on what we started yesterday, and then um, I will introduce something new. I'm hoping by the third session we can start working with the key card. At least I'll take you through how to work with the key card. And tomorrow's session we will start with the project and every other electronic concepts or fundamentals that need explanation. I'm going to do it along, right? The things that I've covered so far are um, some basics that you need right from the beginning to even start building your circuit. Okay, so the rest of the things we will deal with them as and when we get to them or we encounter them. So yesterday we talked in the previous sessions. We have primarily talked about charges. We talked about voltage, electric current, electric energy, and all those things, right? Okay, so the last thing that we're going to talk in terms of properties of material is what we call capacitance. So today we're going to start with that, and then we continue from there. Okay. All right. So as usual, let's perform a simple. Should I call it this? Not necessarily a theoretical experiment, right? This is actually a real thing. So let's take two plates, right? So in here we have the first plate and we have the second plate. Now this plate is conductive. So let's say that it is made up of copper plate and then we have flattened it like that. Now the area of each of these plates, okay, the surface area of each of these plates we will call A, and the distance of separation between them, okay, so from the top part of this plate to the bottom part of the other, we will call D. Is that okay? Now we are also going to assume that this plate is actually very thin in terms of thickness, okay, so take it as something like a sheet of paper, okay, so an aluminum metal that has been flattened into something like a sheet of paper. Okay, so with this point established, one thing that we know is that since these materials or plates are electrically neutral, that is, they have equal number of positive charge and negative charges. We talked about this in the previous session. They will remain neutral. That means even if I put them together, there's not going to be any form of charge buildup. There's not going to be any form of electric field and coulombic repulsion or attraction. Nothing will happen. They are basically electrically neutral. Okay, so we talked much about these things yesterday. Okay, so basically everything that I've said is here. Now let us connect a battery to these plates like that, okay, using another set of copper wires, and then initially we are setting the battery's voltage level to zero. Is that okay? Now take note, setting the battery voltage to zero simply means that the battery has no charges at the anode or the cathode. So just assume that for a moment this is a possible thing that we can do physically, right? We can connect a battery and then switch it off. So this is more like we've connected the battery but we have switched it off, okay? So far as the battery has no voltage on it, again the whole system remains what? Electrically neutral. And of course there is nothing interesting to do with it. Is that okay? Now what do you think would happen if we start to, or if this battery begins to release charges? Mhm. If the battery begins to, let's say the chemical reaction process kicks in, and then the battery begins to release energy or build up energy by releasing electrons at the cathode and stripping them off at the anode, what do you think would begin to happen? Okay, so let's look at that. Now, before we get to that, let's recall some stuff that we need. Yesterday or in the previous sessions, we said that charges on a conducting surface will always spread out uniformly if the geometry allows it, right? Because when you put charges on a surface, they have, depending if they are the same charges of the same kind, then they begin to repel each other. Okay, so the repulsion will move the charges distances apart until there is no more room to occupy, then they will attain equilibrium. Is that okay? So that is one thing that we know, that when we put this battery begins to develop charge, the charge is going to spread. That means that much of it is also going to spread over this plate. So since the negative side is connected to the cathode, more electrons would accumulate or would spread over this base plate. And since we have the anode here, it means that we're going to have the positive charges spreading over here. Is that okay? Now, take note that by saying positive charges, we've already established the fact that these positive charges are actually ion cores, right? So technically they don't move, but then because this copper has electrons and the electrons can move, what will happen is that these electrons on the copper plate would be attracted by the positive plate, the anode terminal. Okay, meaning that instead of having electron deficiency at the anode side, those electrons will rather move to, fill this place up. Okay, and then rather we will have the absence of electrons building up over here. So in essence, it will be like apparently the positive charges moved from here to here, but take note that the positive charges that we are talking about are not mobile. They are just ion cores, right? But then because the electrons rather move, they end up rather leaving positive charges here. So it's almost like the positive charges moved from here to here. Is that okay? Now, for the time being, these things that I'm saying, we are assuming that this distance d between the plate is so wide, right? So wide apart. And so in that case, we will still have some form of equipotential surface. And yesterday we said that it doesn't, is charges don't, energy is not spent to move charges over an equipotential surface, because for energy to move, there has to be a potential gradient. And in this particular setup, we don't have any potential gradient. And now I keep repeating, the main assumption I'm making at this point is that this distance d is so wide apart. We know that for electric field and even the Coulomb force, the wider or the higher the separation, the weaker the forces. Is that okay? Great. So the same thing is going to happen on the base side. For the base side, since we are talking about electrons, right? The electrons are going to spread, and we know that excess electrons causes the atoms to become negatively charged. Is that okay? So once they are accumulating and spreading, they will be attaching themselves to some ions, some atoms, causing those atoms to gain some positive and negative one charges here and there, right? And remember, these atoms also don't move. They are fixed at the crystal lattices. So once an electron attaches itself to those to any atom, that atom immediately becomes negatively charged, but this negatively charged is not mobile. Is that okay? Great. Now, what will happen if we bring these plates closer to each other? Okay, what would happen? Initially, we are assuming that the distance of separation is so wide so that the electric field effect is almost nothing consequential or nothing important, right? So what would happen if we we bring the plates closer together, let's say to about the separation of 6 millimeters. Okay, now that is very close. Now it happens that when that happens, okay, in fact, when we bring the plates together, something interesting begins to happen. Electric field develops between the charges on the top plate, the anode plate, and the charges on the cathode plate. And we know that when electric field builds up, that means energy would be stored in the field, right? Now, when this happens, that means that these charges, or yes, these charges that were primarily supposed to be on the battery's terminal have migrated here. Now, for the time being, forget about whatever is going on in the battery. Let's assume the battery can't change it. The fields that we are talking about, the charges that we are talking about, were the defaults that came with the battery, right? And the battery does not have any means to replace them. Is that okay? So this is going to happen, and energy is going to build up through here. So that means that technically these charges would be the charges that were originally forming the cathode and the anode terminals, right? So the moment this happens, then there is a disturbance. Remember yesterday we said that the battery makes sure that there is charge neutrality. Is that okay? So if there is charge neutrality, then something else has to what happen, because this setup here forming over here would require energy to happen. Okay, so because the battery cannot allow its charges to actually move away from it, because it has to make sure it sustains that potential, that means that the battery is going to do more work. It's going to do more, allow more chemical reactions to what occur, and by so doing, these chemical reactions are going to replenish, okay, or replace the charges that were lost from here. Okay, now this, I'm just trying to, all right, so I just realized that I lost my connection, so let me go over this again. So initially the assumption was that the plates, okay, the battery has developed potential and the plates are wide apart, right? Now we are trying to
Sorry to
bring,
interrupt, but we cannot see the slide.
okay, all right, just a moment. Okay, so the initial assumption, the moment we released the energy, right? The battery started producing energy. The assumption was that the plates are wide apart or far apart. Is that okay? And we know that electric field is actually affected by distance. Okay, so the farther the plates are, the weaker the electric field is. Now, let us assume that the plates are so wide apart to the extent that the electric field effect cannot even be felt, or is insignificant, right? Great. So in that case, we would have the two copper plates would be at an will form an equipotential, or will be at the same potential with the anode. So electrons, as we talked about yesterday, charges will move about without spending energy. Is that okay? True. That is about another scenario. Now take consider a situation where we now bring these plates so close together to, let's say, a distance of about 6 mm, right? When this happens, what would happen? Is there going to be a change in configuration? Is something else going to happen more than we already know? So let us look at that scenario. Okay, so as you can see here, the battery has been set to about 1.5 volt, and then we have charges distributed over the plates. Is that okay? So right now, because the plates are so close together, when we bring the charges on top begins to attract the charges on the bottom plate, right? Because this is what we know. We learned this yesterday, that when there is a force, there is Coulomb force between charges, such that the charges cannot move to neutralize each other. then we have a field building between them. So because of this space or physical separation between the charges, between the plates, the electrons on the negative plate cannot move to neutralize the uh, positive charges on the positive plate, right? So what will happen is that this field will generate, and we know that electric field builds up with energy, and that energy gets stored in the field. Is that okay? So if there is a field building here and there is energy building here, that energy should come from somewhere, right? Now, for the moment, assume that the battery just came with a certain amount of electric field, electric amount of charges, right? And it can no more undergo any more chemical reaction. Is that okay? So if such a thing happens, then we can look at it in the sense that the charges that were previously at the anode and the cathode migrated to fill this the to occupy the or to build up on the plates. Is that okay? Good. But we know that definitely that's not what's going to happen. Okay? That's not what's going to happen. Now, one thing you should also take note is that because of the potential that exists between these charges, the charges have become trapped. Okay? The charges have become what? Trapped. Now, take it as a situation where you have two pair of shoes, or let's say you have just one pair of shoe, right? And then you unfortunately left it somewhere in a friend's house, right? That means your friend right now has those two shoes. Okay, so once you are not in your friend's house, you have to make sure you get another pair of shoes for yourself. Is that okay? So let's assume that the charges that built up on this plate are what were previously on the cathode and the anode plates, right, of the battery. Okay, but then we know that a battery's job is one supposed to make sure it it has the potential at the anode and the cathode. There is a potential between the anode and the cathode, and it also sustains it. Okay, so that means that naturally the battery is not going to allow this to happen. Okay, but it can't also stop it in the first place, right? So what will happen? What is going to happen is that the battery is now going to allow more, is going to allow chemical reaction to proceed to strip more electrons from this guy to build up another potential. Is that okay? Now, I'm just talking about this so that you would understand what is happening. All these things that we are talking about happens at the same time or simultaneously. Is that okay? So technically, we can also say that as the potential is building up on this, the battery would be working in order to maintain whatever potential it keeps at the anode and the cathode. Okay, so that means any excess electron that gets generated out of the chemical reaction comes to fill up the plates. Okay, and we know that before an electron will move, work has to be done, or if I put it in another way, electron moves in response to energy flow. Is that okay? That means that the electrons moved because as the chemical reaction proceeds, electrical energy flowed from the battery. So if the electrical energy flowed from the battery and there is no device here, remember that there is physical space between them, right? So technically it gets blocked, right? So if it has moved and it is not as if it is powering any device, then what would happen to that energy? I don't know if you are getting it. Electrons, as we learned previously, move in response to the flow of energy, right? Now, if you look at this setup, we don't have any electrical load that is going to consume that energy. Okay, so if the energy has moved, then what happens to that energy? Okay, what happens to that energy? Now, let me also mention to you that Once energy is moved from the battery, okay, it cannot, once energy is moved from the battery, it cannot go back. Any energy that is released by the battery would have to, oh, why I am anytime energy is released from the battery, it has to either be used up, transmitted, or stored. Is that okay? So if we are saying that this particular setup actually causes energy to be moved from the battery, and there is nothing here using that energy, then the only other option is that that energy should be stored. Is that okay? So actually, yes, that is what happens in this setup. The energy gets stored in the field. Okay, so this setup here is a way of storing electric energy in circuits. Okay, so now let's go through the notes. So we learned previously that energy that is the energy that is used to move the charges gets stored in the electric field. We know this, right? So although the plates are physically separated, the moment the battery is connected, we will observe some current flow. Okay, so we have a physical space between this plate, but then if we hook up an ammeter and connect the battery, we will see briefly that there will be current flow. So the question you ask yourself is, if there is no clue, the circuit is no clues, why then is current flowing? Okay, that is question number one. Why is the current flowing if the circuit is what is closed? So what happens is that that current that flows is because of the energy that is being released, and that current goes to build up the charges on the plate, and the energy that is released gets stored within the electric field that develops between the plates. Is that okay? So two things: the current that moves, where does it go? It goes to build up on the plates. The energy that moves with the current, what happens to it? It gets stored in the plates. Is that okay? So that means the plate actually becomes the two plates becomes something like its own battery. Okay, it forms something like a battery. So it's like we formed a battery from another battery. Okay, just that we won't call this a battery. So for now, we will just call it an energy storage. Is that okay? So we call it the plate has kind of moved some of the energy from the battery to store it. And the process that causes this to happen is as I have explained. Is that okay? We bring the plates together, charges get trapped, and when charges get trapped, energy, electric field has to build. Electric field is always associated with energy storage. Okay? Now let's continue. So in electronics or in physics, the ability for these plates to store the electrical charge or energy is the property that we call capacitance. And I know by saying capacitance, something else have come to your mind right now. Okay? Now, take note that the battery had to release extra energy. And remember, why I already explained why the battery had to release extra energy, because the charges that moved is different from the charges that are required to keep the battery's potential, right? That means extra charges have to be released. Okay, so that is why there had to be an energy release, and it comes with what, an associated flow of charge. Is that okay? So the battery had to release extra energy to build up the charges on this plate, right? And like I said initially, once energy is removed from the battery, it cannot be put back into the battery. Okay, so take the battery as a one-way valve for energy. You can only take it out, you can't put it back. You can only what, take it out, you can't put it back. So once the energy comes somewhere, and we know that energy always have to be conserved, right? So this energy cannot just come and vanish into a vacuum. Okay, it has to do some work. And fortunately, over here, we don't have any work to be done here. We don't have any device to power. So the only explanation is that that energy gets stored between these plates. Is that okay? So once energy is released, it can be stored, transmitted, or converted to other forms of energy. Now, for our setup here, the only explanation is that it gets what? Stored. Is that okay? So if the energy gets stored and it can't be taken back, that means that the moment we disconnect this battery from the plate, the energy should still remain between the plates. Okay? It's not as if that when we try to disconnect, the energy will have to rush back into the battery. No. Remember, the battery had to release this energy as an extra for to be stored between the plate. So if we take the battery away, if we disconnect it, as you can see here, that energy gets stored between the plate, and in fact, the energy will keep being stored within the plate. Is that okay? So, like I said, the ability for the plate to store this electrical energy is what we call capacitance. Okay. Now, I think I repeated. Yeah, sorry, I repeated this slide. Okay. Now, so energy getting stored between the plates for how long? Well, theoretically, this energy can be there forever unless it is used. Okay. However, as always, we are dealing with physical systems, and the physical systems are imperfect, right? So even if we leave this plate there untouched, things happening in its environment, defects in its materials will cause this energy to deplete over time. Okay, so give yourself some days, some weeks, some months. If you check the energy level, or if you measure the voltage across this parallel plate capacitor, parallel plate, you realize that it will keep decreasing until there is no more. Okay, so theoretically this energy should have stayed forever until used, but physically, because systems, components, and materials are not perfect, we still get some leakages, which eventually leads to what? Depletion of the built charges. Okay, so if we connect a load like a lamp that matches the voltage of the that has built up on the plate, what will happen is that that energy that was in the that has was stored between the plates would actually go in to power up the lamp. Okay, so the lamp would use that energy and it will make it die off briefly. In fact, this is actually a physical thing that happens in circuits. Okay, so let me give you an example. Sometimes some of the laptop chargers, they come with a small light on them, chargers, or even our phone chargers, some of them come with a small LED light on them, right? The moment you plug it into the light, into the socket or something, it turns on. That light will turn on. But when you disconnect it, it takes some time for that light to gradually die off. Okay, that what is happening was because previously something stored some of the energy, and once the main power source was disconnected, that energy that was stored now gets used up, as I'm showing in this animation, right? So in the animation you can see that right now the energy is being used up, which is shown by the charge depleting. Is that okay? Then eventually the bulb goes up, it connects back to the battery, it charges up, we connect it back to the bulb, and then it gets used up. Is that okay? So we can use this technique as a means of storing energy within our circuits. Okay, and I said the property or the ability for anything to undergo store this kind of charge in a form of electric field is what we call capacitance. Is that okay? Now, capacitance is measured in unit of farads. As I said, in physics and in science, we associate units to quantities, right? And again, farads was also named after Michael Faraday. Okay, now this setup that we have here, okay, having two plates with energy built between them, or electric field between them, we call it the parallel plate capacitor. Now you should also know that you should take note that this is a simplification. Okay, this is a simplification for the purpose of teaching. Okay, it's a simplification. Now, so the ability to store charge in electric energy is a very important concept when it comes to electronics. Okay, this is a very important thing. Now I've put here from this particular slide on what I have put all the formulas that you need to deal with capacitance. Okay, so capacitance by itself can be calculated. So it has a symbol C, and to measure the capacitance of any parallel plate or whatever, it is about Q, the amount of charge that has built up divided by the voltage between the plates. Okay, and the energy that gets stored in the capacitor, remember we said energy gets moved and it gets stored within the capacitor. That energy is given by this equation, and then we can also express the energy in terms of the charges as this. We can also express the voltage build up as this. Okay, so these are basically the various ways that we can define, we can manipulate the capacitance in this. We can manipulate capacitance. Yeah, let me just put it that way. Okay, so that is basically what capacitance is, and I'm going to end the concepts here because we have already spent 4 sessions on that. Okay, now the next thing that we're going to look at is how do these concepts that we've laid out benefit us? How do we apply them in circuitry? What are their applications in terms of devices, making devices and all that? Okay, so as usual,